Okay, so chapter 15, quotient groups. So this is kind of what Marinho was asking about. Like we had an abruption in continuity of like why we're talking about cosets and homomorphisms and all those things. Now the answer is clear. Is because we need those things to understand this thing. And I'm not gonna lie, there's a lot of burden on the reader. Like you have to remember so many properties. So I'm gonna ask them questions along the way, because then I can try to understand better uh, why some steps can be done. Okay, cool. So what are we gonna be learning today? We're gonna be learning about constructing all the homomorphic images of any group. So that's what we're gonna be learning. And at first glance, this sounds kind of impossible, right? So how are we gonna do that? Uh, okay, to talk about that, we need to talk back to normal subgroups, which are close in respect to conjugates. We talked about this before. And there's also cosets involved, because theorem 1 states if H is a normal subgroup of G, then AH equals to HA for every A in G. In other words, there's no distinction between left and right cosets for a normal subgroup. What the heck is a subgroup closed with respect to conjugates? Easy enough. Um, if X is any element, um, well, actually, before I read that, it's the thing about the conjugates being in the subgroup itself, right? So if you have an A and you're gonna like do the sandwich thing with the inverse, that element is in the subgroup. That's what that means. So how are we gonna prove this thing? If X is any element of AH, then we know that X can be described in this manner. Makes sense, right? Because again, cosets, it means that we are like applying the operation across the entire subgroup, fixing the element. Um, where H is closed with respect to conjugates, which means that we also know that this is in there because that's the definition of it, right? Thus, we know that we can describe X as we said before, but we can also say that this is valid. Why did I? Okay, we are replacing. Okay, why? Okay, this is my first dumb question. Why can we just say this is true? I guess.
Because if you look at just the two rightmost elements in isolation, they are clearly equal to identity.
You said the rightmost.
Yes, because it's A inverse A that's equal to identity, right?
No, yes, but I don't know if I. Okay. So if you get rid of the parentheses and you just do these two elements, this is identity, which means that we are back to where we started.
Yeah.
Okay, I see. Is it okay? But why is this? Why does this matter? Because if we know this is there, and we also know that this is in H, like capital H, this means that X. Well, that mean, and we get this. This means that X is an element of HA, which is the right coset, and we started with the left one. This shows that every element of AH is in HA. We can do the reverse and prove the other way. So we say that AH equals to HA. And again, at first glance, it seems kind of useless. But then we continue. Let G be a group and let H be a subgroup of G. There is a way of describing cosets called coset multiplication or coset addition, as we're going to see later, which works as the follows. The coset of A multiplied by the coset of B is defined to be the coset of AB. So kinda similar-ish to the definition of homomorphism. Because if you guys recall, we have to keep the operation holding, right? And this is gonna matter later. So this is this is important. And then it says that this is misleading, right? Because it seems deceptively simple. it is not at all clear that the product of two cosets multiplied together in this fashion is uniquely defined. Remember that HA may be the same coset as HC. If this happens if and only if C is in HA. We've already seen this theorem before. And similarly, HB may be the same coset as HD. Therefore, the product HA-HB is the same as the product HE-HD. Yet, it may easily happen that HAB is not the same coset as HCD. And then I have more dumb questions. So my understanding is that these Greek letters appearing here, they are coming from the previous description of S3.
Yes.
But here's my problem. So I don't clearly remember those members of S3. How do we know that the H of beta after gamma is equal to H identity? How do you know this portion?
Uh, there is a table with the definitions of each of those permutations, like way back in chapter. I don't even recall the number, but you can figure that out using those tables.
Okay. And then you're gonna see that what is this proving really? That this example is trying to prove. If you have a correspondence between like HA and HC, and this happens if C is a member of HA, and we've seen this term before. Uh, we can then say that they are equal, but their parts, like when you combine like when you factor out, right, the H, trying to have the combination of the I guess fixed things, the equality doesn't hold. And the reason is because the outcomes are different, right? So if you have HB and H gamma, they become this thing. This is delta, right?
I think so, yeah.
Non-capital delta. And this is H kappa. If you do those things, you get these values. But if you combine them together, in this case, why is this in this case the operation is composition?
Because permutations are functions.
Oh, that's true. I need to remind myself of that. Permutations are a way to describe functions that we use in this book. True. Okay. Thus, coset multiplication does not work as an operation on the cosets, blah blah blah. The reason is that although H is a subgroup of S3, H is not a normal subgroup of S3. If H were a normal subgroup, coset multiplication would work, which is what we are here for. So then we just say that we have an H, which is a normal subgroup of G. So this normal subgroup is again closed in terms of conjugates. Um, this is a given, and this is also a given. And then we have to reach this part. And the proof is, if HA is equal to HC, then we know that A is a member of HC. Hence, A can be described in this way for some H1 in H. And the same kind of applies for B and D in respect to an H2. Then we grab the multiplication of A and B. We just copy paste their uh, possible potential descriptions. We rearrange the parentheses to write in this way. But we know that CH2 is a member of CH. And because of the previous theorem, we know that this is equal to HC. Thus, we can say that CH2 is equal to H3C for some H3 in H. Yes, yes. This is coming because we know that CH2 is a representation in the left coset, but now we are migrating to the right coset. It may not be the same H. Cool. And then returning to AB, so we were here, but now we know that we can swap CH2 with H3C instead, which can then, because of associativity, can be rewritten in this way, which means that this is a member of HCD. So now we just proven that AB is in there, right? So this it is written in here, which means then that the coset multiplication actually worked, and just because of the theorem one being able to be used, right? So if you are a normal subgroup, this is part of like why I think math is hard. It's not only hard because we are using very high level abstractions, but it's hard because you have to remember of all what all of those names mean. So left coset, right coset, homomorphism, group, subgroup, um, and like it's accumulating really fast. We're now ready to proceed with the construction promised in the beginning of the chapter, which comes to my question. Another next question that I have. Let G be a group and H be a normal subgroup of G. Think of the set which consists of all the cosets of H. This set is conventionally denoted as the symbol G by H. Thus, if HA, HB, HE are cosets of H, then G by H is a set of all the possible, I guess, right cosets. We have just seen that coset multiplication is a valid operation on this set. And then we're going to prove that this is a group. But here's my question. Here's my question. Actually, is the question now? No, I don't think it is. I think it's a little bit down here. Yeah, this is good so far, right? Everybody's good?
Yep.
Okay. So theorem 3. G by H with coset multiplication is a group. So we have to prove associativity, neutral element, inverse. Um, so coset multiplication is associative because, yeah, I have questions on these steps here. So we are trying to go from here all the way to here, and we start by saying that HB with HC is equal to HBC. Are we being able to do this because H is a subgroup?
Uh, because H is a normal subgroup.
Oh wait, this is the coset multiplication operation in this case.
Yeah.
Oh, I think that's actually it because you can then combine the H. Like coset multiplication is already kind of like a factorization of sorts, right? Which is kind of crazy, right? Because we are factorizing groups. Like we're essentially doing even more hardcore arithmetic on groups, which is very weird because these are not things; they are groups of things. It's in their name. So we have HB and HC. So we use the coset multiplication to simplify that to HBC. Then we do it again and rearrange the parentheses. So we have HABC. Rearrange the parentheses again, HABC. Then I guess you can do the other way around because HABC is equal to HAB and HC, which can then like this is all because of coset multiplication holding essentially.
Kinda. The rearrangement of the parentheses and the two middle steps is because of the fact that like ABC is just a normal multiplication in a group, and that's associative.
No, yeah, sure. But at the same time, the real trick shots are kind of like this step and this step. If you
Yeah.
didn't have coset multiplication, like you wouldn't be able to proceed to leverage associativity, right? The identity element of G by H is H, which is equal to H identity, and we know that HA times HE is equal to HA, and the other way around as well for every coset HA. Finally, the inverse of any coset HA is the coset H A inverse because when you multiply by them, well, when you multiply them together and you have coset multiplication, they become this thing and they become this thing. And the other way around is also true. The group G by H is called the factor group or quotient group of G by H. Okay, so this is the beginning of my questions really. So about this factorization process. No, us actually read that theorem 5, so then I can ask that question. So it's like coherent. G by H is an homomorphic image of G. Right? So proof. The most obvious function from G to G by H is the function f, which carries every element to its own coset. So like every element gets multiplied by the subgroup H, which is that like that. This function is homomorphism because f of xy is equal to h of xy, which is equal, because of coset multiplication holding, we can say that this is equal to that, which is in fact this. That means that using this function you can obtain an homomorphic image. EF and F is called the natural homomorphism from G to G by H. Since there is an homomorphism from G onto G by H is an homomorphic image. And now comes the real kicker, I think. When we construct quotient groups of G, we are in fact constructing homomorphic images of G. The quotient group constructions is useful because it is a way of actually manufacturing homomorphic images of any group G. In fact, as we will soon see, it is a way of manufacturing all the homomorphic images of G. Our first example is intended to clarify the details of quotient group construction. So we have integers being the group, and I don't remember what the brackets. Oh, it's for cycling. So we have
Yeah.
the cyclic group 6 subgroup of integers, which consists of all the multiples of 6. Since integers is abelian and every subgroup of an abelian group is normal, yeah, where is this come from? Did we do an exercise? Were you supposed to do an exercise to prove this?
We've seen this a few chapters back, actually.
So we
Although we
already.
also know that the addition on the naturals is abelian, I guess.
Sorry?
Addition on the naturals. It's associative, it's commutative. That's.
Oh, you're talking like. Wait, repetitive?
I think. Well, I think we can just take as a given that the naturals with addition form an abelian group, because addition is associative and commutative and whatnot.
Yeah, but this is not only talking about that. This is talking like saying that integers is
Oh,
abelian I
that
can buy.
every is
Yes.
that every subgroup
This.
is normal.
Yes, this is the real
We
kicker to
did
me.
an exercise last
Yeah,
chapter
I
that
thought,
proved this.
okay, this is probably supposed to be an exercise, but because I have a memory of a fish, I already forgot.
But that's easy to
It's
see because you can commute. If it's abelian, you can commute the x and x minus 1 and cancel it out. So for every element. So any subgroup of
Ah, you're
that group
talking
is going
like
to.
by necessity, the subgroup must be normal if the group is abelian because you can always swap
yeah,
them
because
around
if
and
you
cancel them out
if you
Yes,
try to make a
so
conjugate, you don't get
to get
anything because of
yourself.
commutativity. Yeah.
Yeah, okay, I am a fish, but I got that. That's true. Okay, so therefore we may form the quotient group integers by 6. Well, cycle 6. The elements of this quotient group are all the cosets of the subgroup cycle 6, namely. Okay, so here's what I want. Okay, so this is the beginning of my question. So where is H in this example?
Age is the cyclic subgroup of 6.
Okay, so H is the property we want to factor out. That makes sense because that's going to be repeated at least two more times. So H in this case is the cycle of 6. Okay. These are all the different cosets of cycle 6. Why? Because they wrap around, because this is modulo again, every time. Now the operation on integers is denoted by plus, and therefore we call the operation on the cosets coset addition rather than multiplication. But nothing is changed except the name. For example, all of these things are the same, blah blah blah. And then we have even more abstract notation to talk about cosets with single digits, so that we put like a bar on top of it. So this is like cycle plus 0, cycle plus 1, and then you can form this table here, Which again, like I said, we are doing arithmetic like on groups, um, which is crazy. Like we are saying that this is not a normal 5, this is not a normal 5, but it looks like a 5. Because if you are in modulo 6, 5 plus 5 is 10, which means modulo is 4. But it's misleading because these are all groups. Crazy.
Well,
Like insane.
well, they are apparently in this context they are isomorphic to the numbers under the bars.
Like is this a hint that after all everything that the very great mathematicians were doing, they're just doing 1 plus 1 all the over the place? But the one was like overloaded to the nth degree. Like seems this leads me to that conclusion, right? Like maybe after
Oh,
all, if after you get really smart, you are just doing 1 plus 1 again. Huh? Teve?
I don't know, maybe it's. I was just going to mention that the book actually mentions that this is the one of the rigorous ways of defining modular arithmetic.
No. Well, sure, it is one of the one is considered to be the rigorous way of constructing Z6, which is like modulo 6. I understand that, but at the same time, I'm like, are like is our fate to like have white hair and gray beard and doing 1 plus 1 until we die? Like, is that what we should expect?
It's like that meme of the bell curve with the three guys, and the one in the middle is the one that's wrong.
Because like again, 5 plus 5 is 10, modulo 6 is 4, but there's a bar on it. But again, the overloading is just insane. The reader will perceive immediately that the similarity between this group and modulo 6 on integers makes sense. Okay, so let us repeat. The motive for the quotient group construction is that it gives us a way of actually producing all the homomorphic images of any group G. However, what is even more fascinating about the quotient group construction is that in practical instances we can often choose H so as to factor out unwanted properties of G and preserve in G by H only desirable traits. Desirable meaning whatever we want to investigate. Um, yeah, so I kind of have a problem. Um, with like what are the members of G by H, right? Because here's the thing. We are not talking about elements anymore. We are talking about groups. Is that like I'm not gonna lie, this is cool and all, but is that as useful as knowing as having the members themselves, you know? Because at the end of the day, H is interfering with your ability to understand the members of maybe you want to know the numbers here, you see? But you only have access on this level of granularity to the things on the left. This is the result of G by H, right?
Yeah.
So like, you lose some and you gain some. Uh, okay, so theorem 5. Let G be a group and H a subgroup of G. Then if, well, HA equals to HB if and only if HB inverse is in H, and HA equals to H if and only if A is in H. Yeah, I think we've seen at least this second one on the previous, on the like 2 chapters ago on the cosets. Because H is HE, so like, I don't know. If HA equals HB, then we know that A is in HB. So A can be expressed in those terms for some H in H. Thus, HB inverse is equal to H, which is equal to, well, capital H in this case. So how do we know? We know because we are swapping A by HB, so then the B and the B inverse go to identity, which becomes just H, which means that HB is in H. Well, H A B inverse is in H. Sorry. Then AB B A B inverse equals to H for H in capital H, and therefore we know that A is equal to HB, which is inside H capital HB. Yeah, so again, this is not so surprising. I strongly remember this being in the coset chapter. And now about, well, this proves, well, it follows by property 1 of chapter 13, which is 2 chapters ago, that then if you have one equal, it pollutes everything else, and then they must be the same. This proves the first, and for the second, what I said, which means that you can describe using like this, which is equal to A, which is in H, which proves whatever you wanted to prove before. Well, we are kind of relying, like we are using 1 to prove 2, so that's convenient. For our first example, let G be an abelian group. Yeah, I think we are fucked. It's already 26 minutes and we are not in the exercises. That's tough. Let G be an abelian group and let H consist of all the elements of G which have finite order. So we're just gonna go over an example of what the author means by factorization. So like being able to apply a filter. Actually, being able to find all the results of a given filter for a given filter, it's stronger because in the homomorphisms chapter we already did the filter before. So it is easy to show that H is a subgroup of G.
The details may be supplied by the reader.
Yeah, like fuck that, but okay. Remember that in an abelian group, every subgroup is normal. Yeah, we've seen this before. Hence, H is a normal subgroup of G, and therefore we may form the quotient group G by H. And now we will show that in G by H, no element except the neutral element has finite order, which means that whatever is going to be preserved outside of H is going to be the infinite order element. So it's kind of weird in a sense because you focus on manipulating and massaging H, but what you really want is to keep H out of it, if I understand correctly. Like you're doing finite order to get the infinite people.
Yeah, it's kind of the complement of the
Yeah,
subgroup.
but again, I have a very to me that's confusing because when you have H separated, you can, at the moment that you want to go like more into it, like have the minus 18 and the minus 12, you are fucked, right? Because H is going to be applied. Is my understanding correct? That's one of my questions. Like when if you have H factoring out, like essentially doing like removing the common portions of them, like we do with like numbers. But the moment that you want to have the numbers back, you suffer from the same problem of like you have to reapply H on it.
Yeah, when you do this, you're kind of discarding information because remember, this is not an isomorphism, this is an homomorphism, so it doesn't preserve the structure like perfectly.
Yeah. So that there is information being destroyed. Okay. Okay, but I think my intuition is correct. For
Well,
suppose you
I
by
guess
yes,
my
Stefan.
guess is that this will become a good way of constructing homomorphisms for groups that where doing so is not necessarily obvious, like it is on most properties for the integers. Uh, Although I'm not sure.
Well, maybe it's simpler than that. Maybe there is a use case that you don't have to know the elements from the inside, and only the guys on the left side of the equals is already good enough.
Oh,
Maybe.
there is, which are the same use cases for homomorphisms themselves. Like if you want to prove properties of parities, you don't need the numbers, you just need the parities. And this is a way of getting to that, of constructing those homomorphisms, which for
Well,
integers maybe that's kind of obvious, but I am supposing that will not be obvious for certain examples in the future.
Well, but I think that the parity example, although it was very illustrative and educational, the same question could be applied there. Proving the properties of parity using an homomorphism, like showing that parity is an homomorphism, doesn't really help you to answer the question, is this number odd or even? You see what I'm saying?
Uh, it shows that the properties of parities apply to the integers, for
Yeah, no,
instance.
yeah.
If you have a
What it
non-homomorphism.
talks about is that if you already know the number is an even or an odd number, you can talk about the parity of the outcome after applying the group property, the group operation, which is nice, but I think that the parallel that I'm trying to make is I want this minus 18 there, and in the parity example I want to know if the number is odd, but the homomorphism is not talking about that. It's talking about what happens for this particular property in regards to the group operation. I think yeah, I think you helped me realize that the reason that I'm bothered by this is because homomorphism is trying to answer a different question. And I'm trying to ask the wrong question to it. Like, give me apples, and it's like, man, I only have oranges. What are you talking about? uh, yeah, okay, thank you, Tevo. That was helpful. Um, since the neutral element of g by h is h, we've seen this before, this means that there is an integer different than 0, such that hx to the power of m is equal to h. That is, h xm is equal to h. Wait, since the neutral element of that is h, this means there is m, positive m, such that this is true, and it's not 0. Therefore, by theorem 5, we know that x is, well, that is in theorem 5, that's true. X to the power of m is in h, so m has finite order, say t. How do we know that this, how do we know that this is true? Can somebody help me here? Like this.
uh, you're supposing that hx has finite order, right?
Ah, okay, so this is coming as a follow-up consequence of the premise, which is that this is true.
Yeah.
Okay, then it makes sense. Okay, so the order of an element means how many times you have to apply the element to itself using the operation to get identity, right?
Yeah.
Why do we need the t here if you already have m?
Because the t is coming from the fact that
I believe is the order of xm.
yeah, it's the order of xm. So xm is a thing, and the t is the power you have to take that thing so it gets to
Wait,
identity.
but I am confused. If this is true, isn't x to the power of m equals to identity? Or am I crazy?
Not necessarily, but it
Not
means that
necessarily.
you can multiply it a certain number of times with itself to get identity.
No, but that is my question. You said that if you multiply, like if you have x m times, and you have that as a right coset, that's not going to be equal to identity, so this is true? Like, I'm confused. How can this, okay, let me change the question. How can this be true and x to the power of m is not equal to identity?
We just know that hx to the power of m is equal to h. We don't know that x to the power of m is identity.
But that is the thing. How is this true, this equality true, if that's not the case? That's my question.
Because if xm is cyclic, then it means must reach identity at some point, which means it must actually be the same coset as H. Because if XM is in H, then if
Okay,
the
I
multiples are
I think I see what you're saying. Like, if this is cyclic, but you haven't reached the cycle yet, but that still means that this this is gonna be in H. That's what you're saying? I'm trying. Devo? Hello, Devo? Did I drop?
You did not drop.
no, I am here. I think I am confused by your question. Sorry.
My question is, because what I asked was, how can this be true if xm is not equal to identity? And then you mentioned
Well,
that this may be a cycle, and I'm trying to understand that.
I think it's a bit
Uh,
simpler than that. Like in general, HA and HB can be equal, but A and B can be different, as long as they are both members of the same coset.
If HA
Like if
equals HB, AB may be different, but they will be in the same coset.
yeah,
I guess I guess that is true, right? Because the equality is being overloaded in here, and I think that that was my problem. This is not really like this means we are part of the same coset. We like A and B, they like Marinho said, they may be different, but they are both within the same H coset. Well, right or left coset, I should say. Okay, okay. Tev, you were saying? I think I got it, but you're saying?
uh, I'm well. You can factor that out in such a way that the XMT minus one is going to be in H, and then if multiplying that gets a U identity, then that means XM is in H because identity is in H as well. I'm not sure how to make that clearer though.
No, it is what Marinho said. This equality here is being overloaded. This just means that I am in the coset in this one.
Yes, they are the same coset actually.
Exactly. But that is the thing. They because I was kind of just like being naive about the equality. I forgot that we are already overloading it to say we're not the same, but we are contained within the same coset. Yeah, what Marinho said clicked to me. HA equals to HB. A and B are different, but they are in the same coset. Cool. Thank you. Okay, this explains why we need the t, but then x has finite order, so we know that um, ax is in H. Now, this was according to the hypothesis, right? So that x has finite order, I believe. Yeah. By theorem 5, we know that this is true. So xm has finite order. Say t. Uh, Having finite order means that you're after that this is equal to that. But then x has finite order. Um, okay, so now my question is why xm has finite order? It's saying it's theorem true. Theorem true. Okay, I agree that xm is going to be in H. But why does that mean that xm has finite order? Oh,
XM is going to be in H if it has finite order, actually.
it's saying the opposite.
it's because H was constructed by picking the elements which have finite order.
Okay. Yeah, okay, so it is related to the thing about we need to take care of H and making it have the properties that we are interested in. Makes sense. So now this makes sense as well. Thus, by theorem 5 again, this is the case. This proves that G by H, the only element Hx of finite order is the neutral element H. Let's say again. If H is a subgroup of G which consists of all the elements of G which have finite order, then G by H, in G by H, no element except the neutral one has finite order. Thus, in a sense, we have factored out all the elements of finite order, they are all in H, and produce a quotient group G by H, this is a typo, whose elements all have infinite order, except the neutral element, which necessarily has order 1. And then we go back to the commutators thing, right? So we've seen commutators before, and at first I didn't quite understand what this meant, because I was like, the fewer the commutators, the closer the group is to being an abelian group, right? And I didn't understand that at first, but the reason that this is true is because the commutators, they represent the exceptions in this case, right? So you are not abelian, but some of you guys can commute. Then those are the commutators. And then when you don't have, like, as the exceptions are getting extinct, like you have fewer of them, everybody, so then it's like, when it reaches 0, everybody can do it, so it's abelian. So it's kind of funny in a way. It kind of works on the opposite of natural selection. When they die, then everybody is, like, it's kind of weird.
Yeah, I think it's more so that if you have a commutator and it's different from identity, then that means that the group is not abelian, right?
Yeah, no, exactly, because the commutator is only talking about, like, how should I say? Well, you said different than identity, right? So you have, like, because if this is true for every pair of elements, then the group is abelian, right?
Yeah.
Well, whenever it reaches 0, an abelian group has exactly one commutator. So which commutator are we talking about? This one?
Identity.
That's the one that is
Identity.
equal to identity. Or rather, every commutator in an abelian
Exactly.
group is equal to
That
identity.
is what I'm talking about. It's like everybody becomes commutes with identity, right? That's my understanding. Okay, but let's read a little bit. So you have the commutator, which means that, like, if this is true, if and only if this is true, right? In other words, this reduces to the neutral element whenever A and B commute, and only in that case. And this is why I was talking about exceptions, because this is only talking about two guys. What about the other guys? So this is citing, this is listing what are the exceptions to the non-abelian rule, the commutators. Thus, in an abelian group, all the commutators are equal to E. Exactly, because everybody with everybody, this holds. Because if they are abelian, so this is true. Then this is true. So like I said, the exceptions, they are surviving, and then when they die, this is how like I said, this is how I understood this comment. In a group which is unabelian, the number of distinct commutators must be regarded as a measure of the extent to which G departs from being commutative. Which makes sense, right? If you have, as you have more distinct commutators, that means that you have more exceptions. Like, these are the guys that commute. Everybody else, this is not the rule here.
Actually, these are the guys that don't commute, right? Because the commutator is not identity.
I am confused. If you have a commutator, you have something of this form, right?
On the form on the left, yes. On the left of the equals.
On the left of the equals, you mean identity?
No, on the left, that's on the right.
Oh, sorry, here, this, right?
Yeah.
Well, okay, so now you're calling only this the commutator.
Because that's the commutator, yeah.
Mm-hmm. Okay,
And if that's the
so the
identity, then they
product
actually
is
commute.
called the commutator. Okay, I thought this was the commutator. This being true means that it commutes, but
Well,
that's
this
not
being
true.
true means well, this being true means that A and B always commute because like you can always insert an identity between them and factor that into the commutator, you see?
Yeah, but then this sentence is weird because it's saying that like you're always going to have commutators in the if we're naming the product of the commutator that is, that means that you always going to have there's no notion of having more or less.
There,
The question is how many of those are different from identity? That's the
No,
question.
in this sentence it's mentioning that, but in this one there it's not. But I know, but I understand what I was misunderstanding before. So you're always going to have commutators. The thing of the matter is how many of them differ from identity. If all of them go to identity, that means that you are abelian. If only some of them go to identity, then you have outliers. And the fewer the distinct commutators, the closer the group is to being abelian, right? I think that would be an improvement, right?
Yeah.
Okay.
I mean, it's a set. You don't necessarily need to say that it's distinct, maybe.
No, you
I guess
must,
that is the
because they
thought
are all
process.
the same. They are all identity if you are abelian. You must say that they are different. Like if I have
Oh
an
no,
AB and
rather,
a CD and they are both equal to identity, they are the one and the same.
what I meant is that like you have a set of commutators, so you don't need the word distinct because every element of a set is distinct.
He's not talking about a set.
Eh, well, maybe that is the thought process for the author. I don't know.
I think if you add the word set, this would be better for me because I got confused when I was reading this and I was trying to explain to myself, okay, what does it mean to have fewer commutators? Uh, and anyway, I misunderstood. But I now understand that's what you guys are talking about. Okay, so we'll see in a moment that if H is a superproof of G which contains all the commutators of G, then G by H is abelian. Which is outstanding, isn't it? Like, uh, oh, and I have another question actually. So back to the multiple of 6 example. So this is G by H, right? These 6 guys here are G by H. But let's imagine that this is the abelian G by H, okay? That we are just reading there. So G by H is abelian, but it has H in the middle, which has commutators. So my understanding is that I should ignore that we have H inside of there. Like, are we supposed to abstract out that H is in there and H has commutators, which means that they are not abelian? Like, I think my confusion is like there's levels of it seems that there's levels of abstraction.
Well, at this point you're not really operating on the elements of age, right?
Yeah, I think that answers it. So yeah, we need to like make it opaque when doing this analysis then, because you are up a level and you don't have access to the. It's kind of in a way the same thing of category theory thing. Like we've seen this before, that when you are up a level, it's a trade-off. When you are up, you can talk usually more about more powerful stuff, but you keep losing granularity as you go up. It's not like it's not a stack of glass like everything's transparent. It becomes opaque. Like I remember we talking about this with Maninho in the CT book. I think it's kind of the same principle. Okay, maybe this is a math thing. Um, okay, and this is the same thing for abelian groups. Damn, we have 10 minutes. So is there any exercises that you guys think are worthwhile talking about? Out of all of them, like A, B, C. We can go over 1 hour, that's okay, but let's try to be efficient.
I should probably apologize, but I have not had much time to think about the exercises. I did some, but not many.
Yeah, I also went over them kind of quickly this weekend, but one thing I noticed, we keep coming back to like number theory, like in counts of things, like counts of elements, I
Well,
guess.
I think at the end of the day, like maybe this is like a stretch, but my intuition is telling me that after all, algebra is trying to exploit properties of number theory to talk about groups. Like the fact that we know how to deal with primes in number theory gives us the ability to talk about primes in the like a bunch of numbers at the same time in a single shot. The same thing with modulo. Like again, we are doing arithmetic with groups now. So if you're doing
Yeah.
arithmetic, numbers will appear, like primes will appear. Like so that's my intuition about it.
Finite quotient groups. Yeah, this one is.
No, this is the easiest one. Even I could do that. Insert bell curve mean. Math is about numbers on both sides. Math is about abstract things on the center. Yeah, but that is the thing, Tevo. I think that the abstract things, they, I don't know. I feel they are isomorphic to number things. Like, am I crazy? Like, look at this table. Come on. Like, there are numbers in here, but H is a group. Come on. Like, like, am I crazy saying this? And there's another thing. We already talked about like the neutral element, and now we talked about neutral elements in terms of functions. We're talking about the neutral elements in terms of cosets and subgroups. All of those things are isomorphic to zero, right? Like you have to leverage the operation and the thing. So if you can map things to a number, you can go back and forth, right? So and then that means that you can exploit properties that the numbers have on your abstract things world. So that's why the primes appear and the multiples appear and GCDs appear and all that stuff. To me, the reason they appear is because we can go back to numbers after all. We can just say that H is 0, and who cares? Am I right?
Uh, I mean, you can, but in most cases, when you do that, you're discarding information, which may be information you don't care about. Fair enough, but you are.
No, you are discarding information, Marinho, but at the same time, because you can go over there on the world of the zero, uh, the because that connection is already established, the primes keep coming back. Like it's almost like we like there's an abstraction tower, right? And there are evidence up here that we went from there. That is how I feel. That is my intuition. That why we keep seeing the same things over and over again. Divisors and multiples and GCDs and primes. They keep showing up. Anyway, I think exercise A is kind of boring. Because you just follow. Like actually, let me rephrase that. I love when exercises have examples. Like I love that because it helps me understand. But I think that A in particular, I read the example and I didn't even bother. Any comments about A?
No, as you said, it's kind of boring.
Yeah. Okay, so B talks about pairs, right? And there is a question about in geometrical terms, the elements of the quotient group, and in geometrical terms, the operation of G by H. I have no idea geometrically what that means. Any ideas?
Well, they are slightly different in B1, B2, and B3. Like in B1, you're basically saying, okay, H is like factoring out one of the axes of the
Yes,
plane, right?
yes.
So you just go back to normal number arithmetic, which means geometrically the elements are just points on a line, and
Yeah,
the operation is like,
this is a line. This is the line like 90 degrees or whatever. 180, no, 90 degrees, right? This thing.
It's 45 degrees downwards, isn't it?
yeah, that was right.
45 down. I'm confused because you have a line like this and you're doing this. So, am I crazy? That's 90 degrees. That's 145.
No, 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 no. For each step, like let's think of the integers just because it's easier to visualize, right? If y equals minus x, each step that you take to the right forces you to go one down.
Yeah. And if you start, oh no no no, you said 45 in comparison to 0 on x.
Yes.
I said 9 in comparison to 1.
Well, but those are different groups, right?
No no no, but this is not a line, right? This is not a like a line. This is just plain
Well, we did.
x-axis, right? That's why Tevo
It's
said
a whole.
45.
Yeah, no, no. 45 is 2 actually.
No no no, 45 is true, but this line isn't this like an axis?
Yeah, this is like you are discarding one axis, so you're just left with the other. In
Yeah,
this case, you're discarding.
why?
No, you're discarding x actually.
Wait, but you are keeping x and the 0 is here, and you're saying that all the x's. So how you're discarding x?
Well, that's the h. The quotient group will be left with just the y's.
That's just the h. The quotient groups will be left with just the y's. Why? Why, Marinho?
Because remember, whatever property is shared by every element of h will be absent.
H is what we're excluding, is what I said, and I forgot.
Yeah.
Okay, no, that's correct. We are excluding all the x's, and you're keeping only the y's. Yeah. No, no, okay, so never mind. I was the one confused on that. So these are excluding all of the negative 45-degree lines, right? And this is the same, but kind of like different line. That's fine. Any comments about C? C is actually pretty extensive in my like when I read it. This is like okay, if you have the square, if H is a bunch of squares, then every element of the quotient group is its own inverse. Like you have to really figure out what the heck survives after H is excluding things, right?
Yeah.
Um, okay, so for example, how do you know that if you remove all the squares that everybody is its own inverse? Oh well, of the quotient.
Well, because h will become the identity element of the quotient group, right? That
Yes.
means, that means if the square of every element is mapped to identity,
Yes.
That means every element, when multiplied by itself using the group operation, will just result in the identity in this case.
Which is the definition of inverse.
Yeah.
Got it. Yeah. Yeah. But this again, this is it's mind blowing, isn't it? That we are factorizing groups. We are not saying, okay, you have, I don't know, like when you have like fractions and they are multiplying a common factor, so you put the thing on parentheses on the left. Like this is that, but that's a group. That's so crazy to me. I don't know. Crazy. Um, I wonder if the math people know how much overloading they abuse. Do you guys know if they know?
Uh, Only if they are also computer scientists.
Oh, so you think that if they are just math people, they have no idea?
I mean, they don't have any reason to care, do they?
Um, it's
Or
not
rather,
about
maybe
go
they
go go.
just think those things are all the same thing, so it's not overloading after all.
Well, but that Tevo's comment is more interesting to me than Marinho's because it's not about having to care really. It's like noticing and giving that a name. What I think you meant by that is that they, because they don't care, they never had the necessity of giving that a name. And what Tevo said is that if they, from their point of view, it is one and the same. Again, there's no need for a name, right? That's just common sense. I was talking to a friend yesterday, and I was mentioning to him that I kind of concluded that when you give an idea a name, is that becomes more useful when that is not in the common sense. Because if it is, people will ask you, why are you giving that a name, bro? Like, isn't that just like how things are? And like again, Devo just said that. Like for them, it's just one of the things the same. I am the crazy one by giving it a name. Crazy. And anything on C or that you guys want to highlight?
uh, Not really.
Okay. D.
I mean,
Anybody? Okay. Yes, Maninho.
I was just gonna mention C7 is like it's the whole abelian thing has all the commutators again, except as an exercise this time.
Well, 7B is a little bit different.
7b is different, yes.
What is this trying to say? Let K be a normal subgroup of G and H a normal subgroup of K. It seems like abelianness is transitive. That's my first intuition about that. Okay, any comments about D?
Number theory.
Yeah, no, yeah, we have primes again. Like if every element has finite order and every element of H has finite order, then every element of G has finite order. Wait, this is talking about the opposite actually. Yeah, properties of G determined by properties of that. Okay, so this actually answers my question that I was asking about. Okay, but you cannot go back to the elements. This is proving the opposite, right? So if you know the quotient group properties and you know the factor group property, then you can know about what you actually care, which is crazy. Um, so this one is saying that you know that the quotient group has finite order, and you also know that every element of H has finite order. I'm confused. If G has finite order, well, if the quotient group has finite order, doesn't that mean that H element should have all the infinite ones?
uh,
Am I crazy?
Not necessarily.
But How are we doing
There,
the factorization then?
there could be no infinite ones in G at all.
No, but you don't know that. We want to talk about G by talking about the other two guys. You cannot just assume that. I'm asking like, how is this situation compatible with each other? That's kind of my question. If you know that the quotient has finite order, how can there be survived finite order people in H?
Well, it could be that H, every element of H has finite order, but H doesn't have all of the finite order elements of G.
But isn't that the point of doing factorization, is to grab all of it to make like...
The point is that you could be factoring something else, but it just so happens that every element that matches that something else has finite order, but that's not the property you're trying to factor out.
Okay, then I don't understand how you can say something about G then. In your example, because you're saying that you did a factorization of something else, and it just so happens that these two things are true. How can you say something about G then? Because in your example, this it came to be out of coincidence.
Uh, well, G by H has like G in its construction.
No, sure. So?
So some properties of G may show through that.
Yeah, but we're talking about extremes, money. We're talking every element in every sentence. And you're talking about some, like some properties and stuff.
Okay, let's try to put it this way. If you try to factor out like having finite order, every element of H will have finite order, right?
Yes.
But then every element of G by H except identity will have infinite order.
Yes. So far, so
But
good.
that's not the case. The premise is that every element of G by J has finite order, right?
Okay, so whatever factorization you did, you didn't remove, well, somehow that you managed to make that happen. So reading only this sentence, what would you assume? That H accumulated all the infinite ones, no?
Well, yes, but that may be vacuous.
Sure. But then you read this thing and then you say that actually every element of the factorization is also finite.
Well, as I said, it could be that H also has all of the infinite elements, but there so happens to not be any of them in G. So it's vacuously true that H has every infinite one.
I think that must be the reason then of why we can say about something about G. Because if this is true and this is also true, what you said must be true. No? I think it should be like that, no? Like, okay, you start by this. Okay, H, I would imagine H would have the infinite people, but it doesn't. Then maybe it means that what you said, like, even in G, there's no infinite then, by construction.
Well, yes, the exercises should make a proof of that.
Alright, no, I understand, but I just want to understand how would these two things make sense. It's like that. You read the first, and you refine on the second, and then that implies something.
Yeah.
Okay. If every element of G by H has a square root, and every element of H has a square root, again, it's the same principle. You think, okay, I filtered all the known square root ones, because then in what survived is only the square root ones. But uh, you know that that's not true. Then everybody must be square root. And then there's the prime one. Are P groups, then G is a P group. A group G is called a P group if the order of element G X in G is a power of P. What is you're supposed to prove? This, I guess.
Yeah.
And then we'll have also 4. You can say very strong stuff about these things. Okay, I take that back. If you are in a situation that this is true, like you know something about the quotient and you know something about the denominator, sometimes you can actually say something about the numerator, right?
Yeah.
Yeah, yeah. Okay. Anyway, E. Any comments about E? Still have 3 exercises to go. What does the notation of parentheses mean again? Can somebody remember?
The important bit is not the parentheses, it's actually the colon. This means indexing. Um,
Okay.
yeah, basically it means, okay, if you split G into the cosets of age, how many cosets do you have? That's the index of G by age.
Ah, okay. Okay, I forgot about that. So that if that's equal to m, the order of every element of the quotient is a divisor of m. Wow, that's strong. Any comments about E?
More number theory.
Okay. Any comments about F? Wait. Oh, there is an image. Yeah, the image is here. Okay, F.
The quotient of a group by its center.
At the center of a group G is a normal subgroup C of G consisting of all those elements of G which commute with every element of G. Normal subgroup, okay? All of those elements that commute. Okay, so these are the guys that create the commutators. Yeah. Okay.
These are the guys for which
These are all the
the commut.
exception generators.
Yeah, like these are the guys for which the commutator if any other element is equal to identity, so they commute freely.
Yeah. Yeah, suppose the quotient. No, wait. Well, so if C is equal to G, G is abelian.
If C is equal to G,
If C is equals to G, G
well,
is
C
a billion, yes.
well C is a billion by definition, and if C is equal to G, then yes, G is also a billion.
Yeah. Wait, you said that? Oh yeah, C is abelian because C is also a group in that case. And C is abelian. Okay. Suppose the quotient group C by G by C is a cyclic one. Okay, so not only they commute now, but they are also cyclic. Says it is generated by the element Ca of G by C. Wow, there's a lot of burden, like a lot of names in here. So it's cyclic, commutes, and it is generated by this. For every x in G, there is some integer m such that this is true. I don't know. My head hurts. That's what I know. Any comments about F?
Not really. I like the conclusion though.
Conclude that if G by C is cyclic, which is supposed to be then G is abelian. Okay, so that's okay. Does anybody have any idea how to start that intuition?
Hmm.
The quotient will only the only things that will survive on the quotient are the ones that don't commute, right? Well, don't commute with everybody. Maybe they commute among some people, but not everybody.
Yeah.
Um, what can we okay that and plus there's a cycle. What can we intuitively say about it? They don't commute with
Hmm.
everybody. They may commute with some people, and there is a cycle.
Hmm. Well, if there is a cycle, that means every other coset can be derived from the generator, right?
Why?
Because that's the definition of a cyclic group. You can derive every element from the generator.
Ah, that is true. Okay, but how can we come from that, go from that to a billion? I think we talked about this topic before, cycles and being a billion.
Yeah, like if you go through the steps, like the four exercises, right? One, two, three, and then four. Like I think that's trying to build up your intuition in the logical order. Because that's what one is pointing to, right? It's saying, okay, remember, if it's cyclic, that means you can derive everything from the one. That's the F1, right? And then F2 is like, actually, because of how we constructed the quotient group, that can you can like drill down and say similar things about the elements, not just about the groups.
I think I see what you're saying. Yeah, this is generator talking about. This is talking about the elements themselves in regards to C. Then this is talking about being a billion. Use part 2 to write x equals to that, y equals to that, and remember that C and C prime are in C. Ah, okay. We also need to remember that we can use coset multiplication.
Yeah,
I think this is here to make you remember of that. You're gonna be able to
yeah.
write one in terms of the other because of coset multiplication. And when that happens, somebody's gonna cancel out somebody else, and then this will be true. I'm satisfied with that notion. Uh, any comments about G?
It is asking you to go down memory lane and remember chapter 13.
Yeah, no, like I said, my problem with math is that the whole the stack of necessary things and the build up is very hardcore. And if you don't practice enough, you're not gonna be able to just say, "Oh, sure, I have an elephant memory. I remember chapter 13, palm of my hand." Actually, chapter 13 is the one about cosets, just for everybody to know. I know because I looked back to see what the heck we were talking about in chapter 13. So chapter 13 cosets, chapter 14 are homomorphisms, and now we are here. Makes sense. Um, anyway, any comments about G? So this is talking about some um, topology, I guess, like size of the center thing. So let G be a finite group. Elements A and B in G are called conjugates of one another using tilde. If this is true, which is the same as to say that this thing for some x. The relation tilde is an equivalence relation in G. Can somebody remind me what is the definition of equivalence relation? Reflexivity, symmetry, and fuck,
Transitivity.
transitivity.
Transitivity. Yeah.
Okay. The equivalence class of any element A is called its conjugacy class. the relation should is an equivalence relation, the equivalence class of any element A. Hence, G is partitioned into conjugacy classes. The size of each conjugacy class divides the order of G. Wait, so you're telling me that if you split G into a bunch of H's that are normal in respect to a particular element, then okay. Then it talks about distinct conjugacy classes and let K be their sizes and the size. I don't remember. Are the pipes like modulo? Is this order
That's the order of
of
a
G?
group, which is the number of elements in the group.
Okay. That makes sense. Let G be a group whose order is a power of prime. Yeah, yeah. This, like, there's so many moving parts to this thing, and there's the number theory again. Any comments about G?
Not really.
Okay, and then finally, with almost 30 minutes of overhead, we have H, which is talking about something that makes a lot of people uncomfortable, which is induction. Uh, any comments about H?
I'm kind of surprised that it took this long to introduce the idea of inducting on this order, which is effectively the size of a group, right?
Um, let G be a finite abelian group. We will show that G must contain at least one element of order P for every prime factor P of the order of G. If the order of G is 1, this is true by default since no prime P can be a factor of 1. Next, let order of G be K, and suppose our claim is true for every abelian group whose order is less than K. Then P be a prime factor of K. Take any element different than identity in G. If the order of A is equal to P or a multiple of P, we're done. Yeah, yeah. This is the same sentiment. Yeah, it is induction, like true induction that you see in college, like I should say. Um, okay. Any comments about H?
Not really, no.
Whew. Okay, so next time, chapter 16.